Hello, everyone. Welcome back. Today we're talking about bimolecular nucleophilic substitution, which is also known as SN2. All right, and so SN2 is one of the four primary reactions that make up what I would like to call the simple organic chemistry side of things. So these are four different reactions, the first one being SN2, a couple substitutions, a couple eliminations that we'll talk about. But in order to get into these reactions, the first thing that we have to do is we need to take a trip back in time to one of the earlier lectures and ask ourselves, do you remember Lewis acid-base chemistry? Right, because Lewis acid-base chemistry has returned, right? Just as everything in this class does, it's come back with a vengeance because you may remember Lewis acid-base chemistry being along the lines of, okay, we take something like this alcohol and then AlCl3. And where we talked about how the aluminum is missing an octet. So essentially, the oxygen goes in, it forms a bond to that aluminum, and then it has now that ALO bond, which is then a coordinated complex that is now associated. And back then, we would say that the oxygen in this case, the alcohol, I guess overall, is our Lewis base, and then the aluminum was our Lewis acid, right? But we also had a second name for them that is going to come in handy right now, and that was we called our Lewis bases nucleophiles, right? So this is a nucleophile, and then we call our Lewis acids electrophiles. So welcome these terms back because they are here and they are going to be very important for this lecture. Now, I will remind you that nucleophiles just want to donate electrons, electrophiles want to accept them. But the idea of these warrants the fact that they can have different strengths. And this is something for nucleophiles that we call nucleophilicity. Right? And all this term is essentially the ability for a molecule or atom to act as a nucleophile. Right? So the more nucleophilic something is, the more it wants to donate electrons. Because as a reminder, nucleophile is just something that wants to donate its electrons. Right? An electron donor. So, what this brings up the idea of is something that is nucleophilic, right? We can actually compare if something is going to be a better or a worse nucleophile than something else. An idea of this would be, let's say that we are comparing that alcohol that we looked at, which was a nucleophile beforehand, right? We know it has those lone pairs, which makes it at least able to be a nucleophile. But then the other one is it does have a partial negative charge from a dipole, right? It's pulling electron density towards it, and so it does have a partial negative charge. So that makes it a pretty decent nucleophile. That is until we compare it to something like the same molecule. The only difference is it's now missing a hydrogen, right? This one also has lone pairs, but it is fully negatively charged. Overall, it has more electron density. So we would say that the one on the right is a better nucleophile. Okay? And so one thing that you can usually say about better nucleophiles, especially one like this, is that it is less stable because it has that negative charge. And so it wants to donate electrons to stabilize the charge. And this might seem very familiar, right? Previously, we talked a lot about things with negative charges that want to donate electrons. Those were our Bronsted bases, right? And so essentially what we're seeing here is that nucleophilicity and basicity are tied together. Essentially, as basicity, in terms of Bronsted basicity, increases, so does nucleophilicity, right? And so this is going to be said with an asterisk because it's mostly true, but not always. Okay? But essentially, what we can do with this is we can use some of the knowledge that we have from beforehand because we know that a stronger base is essentially also going to be known as a stronger nucleophile, right? Let's do some examples of this, right? Let's pull up a couple things and ask which is a better nucleophile or which one is more nucleophilic. Okay, we can compare things such as let's say we took a carboxylate, right, a deprotonated carboxylic acid, and we compare that to something like the alkoxide there. So the question is, which of these is a better nucleophile? Well, we know in terms of basicity that the alkoxide is more basic, right? This is because on this other side, this one is less basic due to resonance, right? There is less of a negative charge on that oxygen because it's being shared with the other oxygen there. So the fact that the negative charge is fully concentrated on the one oxygen means that it's more basic. Also, this does end up being a stronger nucleophile, right? So this tracks with that idea that things that are stronger bases are also stronger nucleophiles. Another example of this would be, okay, let's say we did something like NH minus versus an O minus. Which one would be a better nucleophile? Well, we know that generally the nitrogen is more basic, right? And thus it's a stronger nucleophile. We'll also put a little star beside that because we'll talk later why this can do other things. It's not just nucleophilic. But the reason we say that is because the oxygen is less basic due to being more electronegative. And these were rules that we applied back when we were talking about acid-base chemistry, right? We said that in terms of um, electronegativity, things that are less electronegative are better bases. So all rules from acid-base chemistry still apply. And they can help us here identify when something is going to be a better nucleophile. That is, except one. And this one is a little more interesting, and it has to do with size and nucleophilicity. Now, you may remember back where we talked about acid-base chemistry, we said that the bigger something is, the happier it is to act as an acid, right? It likes to get rid of a proton. And if we were comparing something like S minus versus O minus, we would say that the O minus is more basic, right? It's pretty happy to give away those electrons. But the thing that becomes really weird is that if you were to test this, you would find that it's less nucleophilic than the sulfur, right? And so essentially, this is going against everything we've talked about before, right? The bigger something is, normally the more stable it is, which we just talked about instability being useful for nucleophilicity. It's also less basic, therefore it should be less nucleophilic, but it's not. So why is that? Well, it has to do with the idea of the size changing how the atom holds electrons. Because remember last time when we talked about size, we essentially just used it as a platform to say, oh, sulfur versus oxygen. The oxygen has the negative charges much closer, and so there's a lot of electron repulsion, right? So there's more electron repulsion from charge. Versus on the sulfur, they're kind of too far away, right? But the thing is, there's another thing that is happening here that is, it has to do with electronics that matters a lot. And that is, remember that the nucleus is also positively charged for both of these, right? And when this nucleus is positively charged, it's pulling those negatively charged electrons towards it, right? So it's a strong electron attraction to the positively charged nucleus. And so because of that, since they're so much closer with oxygen, that means that those charges are feeling the attraction more. And so we would say that they are held tightly, right? The charge is held tightly and it's happy there, especially with oxygen's electronegativity. Sulfur, on the other hand, these charges are further apart. And if you've taken physics before, you know that it's a square in terms of the radius increasing. The drop off is a square in terms of force felt between the two. And so, with that being said, the sulfur is not holding onto this negative charge very well. It's held very loosely. And since it's held loosely, it wants to donate it, right? It has no reason to hold on to it, right? So, held loosely essentially just says, hey, it wants to donate, which makes it more nucleophilic. So that's why when we're looking at these, size is actually a little different from what you would expect. You would expect size to be worse in terms of nucleophilicity, but the bigger something is, usually the better a nucleophile it is. Okay? So this brings up a important distinction that we have to do here. And that is this idea, we're going to call it strong versus weak nucleophiles. All right? Because we have a scale of nucleophilicity, and it ranges, we'll do from left to right, where the right-hand side is going to be our strongest nucleophile, which I'll be abbreviating NUC. So anytime you see NUC, that means nuke or nucleophile. And then on the left side, we'll have our weakest nucleophile. So on the strong side, we're looking at these things that are usually negatively charged, right? They really like to give away their electrons. So ideas of what that is something like S minus, right? It really wants to give away those electrons. You can think of like a negatively charged carbon is actually a really strong nucleophile because it's not very electronegative, so it wants to give away that negative charge. Things like iodide, right? Very large, wants to give away that negative charge a little bit. Something like um, a negatively charged oxygen. Interestingly, we have a neutral nitrogen, right? So I will say this is an exception to the trend, right? Because it's neutral. And between that and some others is a negatively charged chlorine, right? So you can see that it's a little bit different in terms of where that nitrogen sits. But notice there's no N minus on there. And we'll talk about why in the next couple of lectures. But right between this chlorine and what's next, we're going to put a dividing line, right? Because this dividing line is what I would call the difference between truly weak nucleophiles and truly strong nucleophiles. Okay? And so below this dotted line, we have things like neutral sulfur, right? It doesn't want to give away its electrons that much, so it won't, right? Same thing with neutral oxygens, right? They also won't give away electrons. And then realistically, any other neutral atoms with lone pairs, except for nitrogen. So notice on our side of weak nucleophiles, we always have neutral structures. Versus on the side of strong nucleophiles, almost always they're negatively charged. except nitrogen. Okay? And the reason for this is because all of these nucleophiles um, essentially have one thing in common between the weak and the strong forms, and that is where they start in terms of energy, right? So weak nucleophiles are relatively low energy, right? Because they're usually stable. But then strong nucleophiles are usually unstable, right? So if we draw a nice red dotted line to show the difference, and you can see very easily the difference in energy between these two, right? The fact that one has a negative charge and the other is neutral, it kind of lends to the fact that the negatively charged one would be higher energy and thus less stable, right? So we would say strong nucleophiles are high energy and unstable. Okay. And this is going to come in handy in just a second when we start to talk about SN2 itself. But before we can talk about SN2, we have to talk about the other piece of the concoction that's very important for us here. And those are these things we like to call leaving groups, right? And so leaving groups are atoms or groups of atoms with weak carbon to whatever it is, we'll call it X bonds, which are happily broken. Okay? Essentially, the idea of leaving groups is leaving groups are found on electrophiles, things that really want to take electrons. And the other thing is that they are usually conjugate bases of strong acids. Okay, well, what does this actually look like? Well, we can bring up a couple examples of what this would look like. Take, for example, a reaction that we actually looked at in a previous lecture, right? I believe it was 2 lectures ago. I had shown this one reaction that required this and some water, and essentially I had shown that the first step was this carbon-bromine bond breaking. And the reason for that is it generates this very strong electrophile, right? Because it wants electrons there, but then also it generates Br minus. And we know that Br minus, bromide, is the stable conjugate base of HBr. What that tells us is that it is a good leaving group. And more importantly, that tells us that this bond between the carbon and the bromine is a weak bond, right? This is contrasted with something like an alcohol, right? That OH bond. If we tried to do the same thing with this, right, breaking the bond and giving the electrons to the oxygen, we would make that positively charged carbon, the exact same as we did before. But then we have OH minus, right? And this is an unstable conjugate base, right? And the reason we say that is because it's not a strong acid conjugate base. So we would say that this is a generally bad leaving group, which we're abbreviating LG. That also tells us that the bond here is a strong bond. And remember, all of this is rooted in the idea of what is essentially energy. Because if we were to look at a energy diagram of these two, right, both of them are going to start out as generally the same energy, right? We'll make one blue, so the blue trace will be the OH, the black trace can be the Br. And they're both making the same carbon-containing product. One of them's making Br, the other one's making OH. So the one that's making Br Yeah, it's going to increase in energy because it's making charged stuff, but the one that contains the OH is going to be massively higher in energy for both activation and product formation in terms of enthalpy. Okay? So depending on that stability, that tells you what's a good leaving group. If the activation energy is too high, it's a bad leaving group. Now we'll return to that idea later on and talk about what it means for activation energy to be too high. But for right now, just know that bad leaving groups will have too high of activation energy, and it's because they're usually not conjugate bases of strong acids. So with that being said, we have another range, right, where we can draw from left to right the idea of what is the best leaving group and then what is the worst leaving group. All right. So thinking about good leaving groups, it's all the strong acids, right? So it's also in order of which acid is strongest to which is weakest. So the conjugate base of sulfuric acid is going to be the best leaving group, followed by something like iodide, bromide, chloride, and don't forget about one very important one, which is H2O, right? Not negatively charged oxygen, but remember H3O plus is a strong acid, and so it does fall into the category of the conjugate base is a good leaving group. So all of these are conjugate bases of strong acids. The second we're no longer in that range, we cross a threshold like this here, and we go into the bad leaving group land, right? So I would say that these are bad leaving groups, and I would say the ones over here, these are good leaving groups. Okay? And so looking over here, just across the line, we have things that are not strong acid conjugate bases. And the first one that people always look at is fluoride, F minus. Remember HF, even though it is a acid of a halogen, fluoride itself is not very stable. All right. So because of that, HF is not a strong acid. It is a weak acid. All right. And that is why F minus falls into this category. Same thing with other negatively charged things such as SH, OH, NH2 minus, right? All of these are not as stable as the good leaving groups. They are both enthalpically and kinetically disfavored. Okay? So, with that idea in mind of what a good leaving group is, what a good nucleophile is, we introduce bimolecular nucleophilic substitution, or SN2 for short. And SN2 requires two things, right? It requires, first off, a good, strong nucleophile, right? That is one of its needs. The second thing it needs is a good leaving group. If you do not have both of these, you will not end up seeing an SN2 reaction occur. It is not possible. So what does this reaction actually look like? Well, essentially what you do is you're going to take your nucleophile, right? And remember, since it's strong, it's usually going to have a negative charge. You're going to mix it with some carbon that's attached to a leaving group. And what it's going to do is it's going to perform a substitution reaction. So the nucleophile is going to come and form a bond with the carbon, and it's going to break the bond between the carbon and the leaving group, right? We call this a nucleophilic attack, right? Because the nucleophile is going and giving its electrons to the carbon and forcing the leaving group to leave. And so what ends up happening is now what we've done is we've formed the bond between the carbon and the nucleophile, and we've broken the bond between the carbon and the leaving group. And so this reaction right here is the SN2 reaction. All right. Here's the thing. It is a single step. Okay. So it is concerted, which essentially means a single step. And the other thing is it's a backside attack, which means that the angle of attack is 180 degrees to the leaving group. On the exact opposite side. So what does that actually look like for us? Well, if we were to draw this structure out in its actual orientation, right, it's tetrahedral. So looking at it, we would see something like this, where our nucleophile would position itself 180 degrees from the leaving group. It would come in and it would attack right there, and it would kick out the leaving group. And so notice where that arrow is. If we were to just draw an angle between it, that's completely linear, 180 degrees. But what this does is it forces everything else to kind of flip, right? So these hydrogens that are over here are then, in order to retain 180, or sorry, 109.5 bond degree angles, they're going to have to move. And so what this ends up doing is at the end of this reaction, your nucleophile is on the side that it came in at, but those hydrogens, or whatever it is, got pushed over to this side, right? You can think of it kind of like when your umbrella flips inside out, all right? Because what that does is it just essentially makes every group kind of change their positions and where they are. Okay, so the reaction's pretty nifty. But the thing is, we kind of have to now think about it in terms of energy, right? Because energy is always important for everything we talk about from here on out. And so for the energy of this reaction, if we're thinking about the one that we have shown here, we can draw an energy diagram where essentially the reaction progress, we don't have to worry about intermediates, but we start out with the nucleophile with a negative charge. And then we end up with the leaving group with the negative charge, right? Which is part of our products. And this was part of our reactants. But overall, we are coming in, we're breaking that bond, and we're kicking out the leaving group, and we're forming a more stable final product. Okay? And looking at this energy diagram, we've got this delta H as being negative, but we also do have a pretty high activation energy barrier. Okay? So the first thing we need to discuss is for any strong nucleophile and good leaving group, the delta H is going to be negative. All right? The question is why? And very simply, you can think about it this way. Think if we started the reaction out with OH minus, right, hydroxide as our strong nucleophile, we would say that it's relatively unstable, right? Versus we come in and we have bromide, right? It's a good leaving group because it's very stable. If we're moving from unstable to stable, that is always going to be a favorable delta H, which is negative, right? That being said, that doesn't account for our activation energy though. And this one has a high activation energy barrier. And the question becomes, why is that? Well, think about the other lectures that we've gone through so far. A high activation energy barrier is usually due to an unstable transition state, right? So let's take a look at what this transition state looks like. Since this is all happening at once, we actually have a really interesting transition state on our hands because the nucleophile in the leaving group will still have partial bonds when the transition state happens. The flip is also occurring at the same time as the transition state. So what we actually end up seeing for an SN2 transition state is that the transition state consists of the carbon that is being attacked. It has those three groups attached to it, right? Whatever those three groups may be. The leaving group is currently breaking the bond to the carbon, and the nucleophile is currently forming the bond to the carbon. Of course, these all have partial negative charges on both the leaving group and the nucleophile, because remember when we're drawing transition states, it's where the charges end up, and the nucleophile starts with a negative, and then the leaving group ends up with the negative. If we're using Hammond's postulate, we can also label some things, right? Because it looks more like the reactants. So this bond to the leaving group should be short because it's mostly associated. This one to the nucleophile should be long. But here's the thing. Notice that the reason that this is so unstable is primarily due to the shape, right? Notice what it looks like around that carbon. The carbon looks like it has five bonds, right? And we know that is not very stable. We would say that this transition state is trigonal pyramidal, right? And the trigonal pyramidal transition state has not enough space for everything, right? Carbon is meant to have four bonds around it, and it having quote unquote five means there's not enough space for all of the bonded substituents. This leads to unusually high steric strain as well as bond angle strain, right? All of these things want to be in a certain position, but they're each bumping each other out of the way. Okay? But the thing is, this is an SN2 transition state with actually not a ton of steric strain. It's not that bad. Adding groups, though, causes problems. All right, so we'll say more groups equals more problems. The reason for this is think about it. Let's say we had a primary carbon. Because remember, this one up here just had hydrogens in the leaving group attached, so it's technically just a methyl type carbon. It's not even primary. The second we move to primary, we would see that let's say that this one up here is the carbon with the substitution, and we just made it a CH3 for the sake of it. Well, CH3 is not small, right? And so what that does is in our transition state, now as the nucleophile approaches, it actually ends up having a steric interaction with the CH3 because those hydrogens are sticking out there and they're a little bulky. But then if we take this and we think about it in terms of a secondary, what would that look like? Well, in a secondary case, it becomes even worse because that one CH3 now becomes two. And what we're doing is we're crowding out the position of the nucleophile as it wants to come in and perform this substitution, right? So in this case, we now have even more steric strain because not only is it the one from above, once again, pushing the nucleophile away, it's the one from below pushing the nucleophile away. So this is even higher energy. Not to mention, the tertiary has three cases of high steric repulsion. And so what this means is the more bulky groups that are around that carbon, it's less stable for the transition state, and thus a higher activation energy. Now, what does this look like in terms of an energy diagram? Well, we can actually demonstrate this using a couple different colors when talking about our reaction progress. Because here's the thing. For these, let's assume that the nucleophile and the leaving group are always the same. If that's the case, essentially what we'll do is we'll give each of these a color. So let's just say the first one's the CH3 with the leaving group. Second one is primary. Next one is secondary. And then we'll have pink for the old tertiary. Okay. All of them actually start and end at the exact same point, right? Because in this situation, if the nucleophile and the leaving group are the same, the energies of the bonds formed and broken are very similar, right? So the delta H is essentially equal for all of these, okay? The difference comes in those activation energies, where in the first one, it has a relatively mediocre activation energy, but we've added in that steric group for the primary, and its activation energy starts to skyrocket. But that's not the only one that starts to skyrocket. The secondary also gets quite high. And then we have the tertiary. And let me tell you, the tertiary, we're just going to cut it off there and draw it back in right here because tertiary has an astronomical activation energy. It is so sterically bulky, it's just huge. So notice how as we go from one to another, this activation energy gets almost exponentially larger. And this tells us something about the rate of substitution, right? So the rate of SN2 is fully dependent on this idea, where something like the CH3 with the leaving group is much faster than a primary, which is much faster than a secondary, which, as we saw with that tertiary, is astronomically faster than the tertiary. So what we're seeing here is essentially these first three, these can occur just with different rates, right? Where the CH3 leaving group, this one would be our fastest. And then, of course, the tertiary would by far be the slowest. That being said, there's one thing about SN2 that's really important, which is tertiary is so slow, it is actually not possible to perform SN2 on a tertiary carbon. It is just so slow that it's not even possible for the reaction to occur. Okay? So that is another thing about SN2 you need to keep in mind. The substitution of the carbon that you're looking at that has the leaving group attached, depending on how substituted it is, it's going to change the rate. And you can't even do it on tertiary carbons. Okay? Now then, that being said, the next thing we need to talk about is how is that rate calculated? Right? So we can look at some rate law for SN2. Now, you haven't talked about rate laws since Gen Chem, and that's because for the most part we stay away from them. But rate law is something else that we actually need to keep in mind when we're thinking about reactions. And the first thing that's really important for rate laws is that the rate law is determined by the rate determining step. Funny enough, this is something that you also talked about in Gen Chem, right? The rate determining step, aka the slow step, is the one that tells you what the rate law is going to be. And in this case, if we're thinking about an SN2, the SN2 reaction is very simply a single step, right? So let's say that we're looking at that original one that we were talking about beforehand, all it does is it comes in, does a backside attack, kicks it out in a concerted manner. And that concerted manner tells us that if there's only one singular step in the reaction, the single step must be the rate determining step, right? Also known as the RDS. Okay, if that's the case, how does rate law and the rate determining step come into account? Well, the way that happens is essentially the rate determining step, whatever's involved with it is involved in the rate law. So as a reminder, rate laws essentially say the rate is K times the concentration of something. We'll say X in this case. For an SN2, the rate of the reaction is dependent on the reactants that come together in the actual substitution step. Okay? Because it's only a single step. So in this case, the rate is determined by the nucleophile concentration times the concentration of the alkyl with the leaving group. And this is where the name for SN2 comes from, right? The name for SN2 is bimolecular nucleophilic substitution. And so these right here are our bimolecular statements because it is two molecules interacting in the rate law. Okay? Now, that being said, we're not going to go over much about the actual rate laws in this course. Instead, we're going to primarily focus on the reactions themselves, and the energies of the reactions. The rate laws can be important, but for us, they're not going to be that important. So don't worry about them for the exam. I just wanted to give this as background so that you understand why it's called bimolecular substitution, because, of course, I don't want there to be any confusion in that. Now, that being said, we're going to move on to the next important thing about our SN2 reaction, which is inversion. So, talking about inversion, you probably saw back when we were talking about the umbrella flip that the flip does interesting things because you may imagine, let's say that we labeled a structure in terms of priority, right? Let's say the leaving group happened to be priority number one, and then we just had two, three, and four like this. Well, when our nucleophile comes in, as we had drawn out before, it's going to come in, it's going to do a direct backside attack to kick out the leaving group. And let's say that, we end up with now the nucleophile is here, and let's say that it took the new number one. But everything else, remember the umbrella flips, so these other groups get pushed over here, but they're still in the same positions, right? Two is still on the thing in plane, four is still on the dash, three is still on the wedge. Well, notice if we were to draw to find absolute configuration by our one, twos, and threes, drawing an arrow from one to two to three, that's counterclockwise and four is on the dash, we would say this is S. Whereas over here, one to two to three, that is clockwise, this is R. What this is showing us is that the SN2 reaction inverts the stereochemistry. Okay? So it essentially takes the stereochemistry that's there and it flips it. Now, an example of this is going to be like we see here, but keep in mind it's only when it's chiral that it matters, right? Only matters when it's chiral, which was why I didn't use the CH3 example because it wasn't chiral, so there's no difference in R or S. All right, so let's hop in and let's look at a couple examples so that we can get a good idea of what the reaction looks like in practice. All right, so we'll do some examples of SN2. Okay, for the first one that we'll do, let's say that we have this right here. We have a chlorine attached to this alkane, and it comes in with some sodium hydroxide and THF. Now, THF is what we would call a solvent, right? Next lecture, we're going to give a little bit of the solvent dependence of SN2 as well as the solvent dependence of SN1. But for right now, I'm just going to give you the fact that THF, it's a good solvent. What this will do is the chlorine is on a primary carbon, right? Which we know reacts pretty fast for an SN2. So because of that, we can say, all right, what would the mechanism of this look like, right? Because we have to provide that roadmap for what's happening in our reactions. Well, we have our alkyl chloride. We have the sodium, who is a spectator ion. And then we also have our hydroxide, which we know is a strong nucleophile. We also know that chlorine is a good leaving group. So we have our strong nucleophile, or we have our good leaving group. Strong nucleophile is going to come on in. It's going to backside attack, kick out that chlorine. And what we'll end up with is we've substituted the chlorine for the oxygen. Keep in mind the oxygen still has a proton attached to it, so now we have the alcohol. And we've made sodium chloride, right? Because it's just Na plus Cl minus. So overall, this reaction gave us those products. Whoops, not NaOH, NaCl. And keep in mind that since this carbon here has two hydrogens attached, it is achiral, right? So we don't have to worry about stereochemistry. Now that being said, we can do a second example of what an SN2 looks like, where we have something like this, and we bring in something like this here in DMF. So in this case, DMF, another solvent, right? So we don't have to worry about it doing any of the reaction. We then have over on this side a secondary carbon that has the iodide attached to it, right? So this is a secondary alkyl iodide. We know the iodine is a good leaving group. And then looking at our sulfur containing thing, it's an S minus with a K plus, and we know that S minus is a strong nucleophile. So we have everything we need for this reaction to actually occur. Mechanistically, right, if we're looking at the mechanism, what's happening is we have our iodide there. Our S minus is going to come in and perform a backside attack to kick out the iodide. In doing so, notice that the iodine has stereochemistry. It's on a wedge. Since we're attacking from the backside, the complete 180 degree of that would put our sulfur on a dash, right? Keep in mind that this carbon chain is still attached to the sulfur after everything is said and done, right? You need to make sure that you do that. And then we also have Ki as our byproduct. So overall, in this reaction, the wedge inverts to a dash upon substitution, right? So this one is showing that inversion of stereochemistry. So when we're writing our actual products out, that is what we would write. Okay. And now on exams and other things, I would definitely just rather you write out the major product and not the salt byproducts, right? Because this just becomes a spectator after all is said and done. This is the stuff that we actually care about as the major product. It's the thing that was actually substituted on. Okay? So overall, this is the idea of SN2. We're taking a good leaving group, a strong nucleophile, we are adding it in, and as long as we're looking at something that has stereochemistry, it'll do inversion. All right? The other thing is we have to keep in mind that it has to be on a primary, secondary, or the methyl-like carbon, because if we look at example 3, let's say that we were looking at something like this here, right? And we tried to do a substitution with NaOH and DMF, we would see that there would be no substitution reaction that would occur. All right. Now, that being said, it's not like we don't have a good leaving group. This OTS is actually a good leaving group, right? I'll talk about why in just a second. Of course, OH minus is a strong nucleophile. The only issue is we're on a tertiary carbon. And as a reminder, tertiary can't do SN2. So those are some things to keep in mind whenever you're doing these types of reactions. Now, that being said, I did tell you that I was going to talk about that OTS leaving group. And there are two different leaving groups that I just want to bring up very quickly here at the very end. They're called tosylate, also shown as OTS. And the structure of this is this here. And you can imagine that the OTS, right, it's assuming it's connected to something, which would be R. So this, whenever it gets kicked out, it looks like sulfuric acid, right? Same thing with this idea of what is called a mesylate, or OMS. It is also one that just looks like sulfuric acid. So if you see these abbreviations, which you will be seeing a lot more as we go through, just know they're good leaving groups because they look like sulfuric acid. But again, for this week, considering we're starting with SN2, it's not going to be on your next quiz. It is not going to be on your homework assignment. So you do not have to worry as much about stressing for this at the moment. That being said, going to give you a little summary of this lecture as well, because these summaries are going to help you later on make sure that you have everything straight in your notes. The first one is SN2 needs both a strong nucleophile and a good leaving group, right? SN2 occurs faster with less sterics, right? Due to that activation energy we were talking about. SN2 can't occur on tertiary carbons. And finally, SN2 inverts stereochemistry. So next time, what we're going to do is we're going to take this idea of SN2, we're going to keep it in our minds, and then we're going to look at something called unimolecular substitution, or SN1. We're also going to take a little bit of a look at solvent dependence for these reactions because they are affected by the solvent that you run them in. And then overall, we're going to be taking all of that information and using it to continue forward when we move into eliminations. So with that being said, I'll see you next time when we talk about SN1.